Hello, everyone. We are live here on Twitch. My name is Matthew, and I am one of the course staff instructors for our Coursera and Udemy courses. And we are excited to have you here today. There is all sorts of amazing stuff going on in space and astronomy news this week, and we are excited to have you ask questions and talk to you about some of the cool happenings. One of the things we wanted to mention is that we've created a quick video tutorial for anybody who would like to subscribe. One thing that we discovered is that anybody who has an Amazon Prime account can get a free Twitch subscription, which would help us out with our programs, because when we get your support, then we can continue our programs and continue making high quality programs. And so we're going to post the link in the chat, and if anybody has an Amazon Prime subscription and would be interested in subscribing to the channel, that would be fantastic. All right, we're going to start with our an introduction from Professor Impey, and then we'll get right into questions.
Okay, welcome everyone to the online session this week on Twitch and then YouTube. So welcome everyone, and we'll start right away.
All right, the first question is from Roxoa, who asks, can you talk a little bit about the Messier Catalog? Can you talk about what it is, where it came from, and why it's still interesting and talked about today?
Sure. The Messier Catalog needs no introduction to any amateur astronomer because it's almost a central part of their activity. Amateur astronomers love to sometimes quite competitively observe every object in the Messier Catalog that's available in their part in the sky that's visible to them in a single night. That's quite a challenge, actually. Some of them are quite faint. So it's well known to amateur astronomers, not so well to other people. The most familiar objects to most people are Andromeda Galaxy, which is M31, and another bright galaxy, M51. But basically, the Messier Catalog is about 110 objects. The actual total number fluctuated a couple of times because objects went in and out of the catalog at the end. Created by Charles Messier, a French astronomer from the late 18th century. I think the catalog was published in its final form in 1789. Messier was a comet hunter, and he noticed that there were some fuzzy nebulous objects that looked like comets through a small telescope, but which weren't moving, as comets will always do from week to week or night to night. And so he essentially created the catalog as a set of objects for comet hunters to avoid, because they weren't comets but looked comet-like. So it's rather interesting that this catalog, which is a sort of a not catalog, has turned into a foundational catalog for astronomy in general. So these are deep sky objects, but not so deep that you can observe them with small telescopes. M31 you can see with the naked eye from a dark location. And the Messier Catalog is a mixed bag, because things that look fuzzy in the night sky but are not comets can include a variety of things. I think roughly 40% or so of the Messier Catalog are galaxies, so distances of a few million up to tens of millions of light years. Another roughly third are nebulae, which are associated with stars at active stages of their life, so planetary nebulae, for example, or novae, or supernova remnants. And then it's a mixed bag what the rest are. There are all sorts of astronomical objects. So it's a pretty famous catalog, and rightly so.
Excellent. The next question is from one of our live participants. Sharptail Girl would like to know, how are asteroids found? They're so small. Is it always by chance?
No, there are pretty systematic surveys for asteroids, and continuing to this day, there are surveys for asteroids. The asteroid belt, it actually spans quite a large distance between the orbits of Mars and Jupiter. It's not just a thin little strip. It extends over, actually, I think, tens of millions of miles radially out from the sun. And the asteroid belt, of course, includes objects of an enormous range of size, the very small number of objects that are large, and then a vast number that are small. The first asteroid to be detected or discovered was Ceres. People were looking for a planet between the orbits of Mars and Jupiter, and Ceres seemed to be at an appropriate location. It was discovered, I think, in 1803. by Piazzi Smythe, an Italian astronomer. And that's an object of about 1,000 kilometers across. So the biggest asteroids are hundreds of kilometers, but telescopes and surveys have now been able to identify asteroids down to the tens of kilometers and even a few kilometers range. Now, at that distance, beyond the orbit of Mars, something that small is very faint. So these are pretty sensitive telescopes doing that. And there's close, not an infinite number, but there's just a vast number of objects that are smaller than a few kilometers. And so it's essentially an unknown or uncatalogued number. These asteroids are meaningful because we want to know where they came from. We want to know if they were a failed planet. We want to know any asteroids that might leave the asteroid belt or things that came from the asteroid belt that are heading towards the Earth or near the Earth so that we can study them and hopefully so that they don't head right at the Earth and hit us. So the asteroid belt is valuable for a variety of reasons in planetary astronomy.
Excellent. Thank you very much. The next question is from Hernan Reyes, who sent an email and is on with us live, and is very interested in the astrobiology part of our courses. And so it's kind of a complicated question. So let's just start with, he's very interested in thinks almost that it should take precedence the search for a second biological genesis. So life 2.0. So the question is, do you think that is the most important question, even more important than finding life that may be connected to Earth life? And then we'll go from there.
Sure. Second genesis is an interesting topic. Clearly, if we haven't found life anywhere else in the universe than the Earth, so at the moment we're still just looking, and astronomers, of course, would be happy to find any form of life. But if they find life within the solar system, then a simple question arises. Is it life that's identical in its biological and genetic basis to life on Earth? In other words, operates according to DNA coding for proteins with cells that are similar in architecture to ours, in which case that's an interesting discovery. If life is not like ours and is completely different, then that opens a huge box of possibilities out for what life elsewhere in the universe might be like. So that binary distinction of whether the life we potentially find in the solar system is exactly like our life or different is a huge difference maker in astrobiology. The problem comes because if we find life that's different from ours, then clearly it's a second genesis. But if we find life that's identical in basis to ours in the solar system, we do have to ask whether it is a true independent origination, because rocks can travel through the solar system from one planet to another, and potentially they could be life-bearing. And so you have the possibility that life starting one place, like the Earth, could be seeding life elsewhere, or that life on Earth started from life elsewhere. Now, these transmission events of life-bearing rocks don't occur with equal probability. For example, it is much more likely for a rock to be blasted off Mars by a meteor impact and land on the Earth than vice versa, because the Earth has stronger gravity, a thicker atmosphere, and is further out from the sun. So some of the probabilities are low, and some are high, and some are hard to put a number on. But these things are taken into account when we do find a second version of life. And the other issue is, of course, that our primitive technologies are really unlikely to be able to say whether life is identical genetically to life on Earth for the foreseeable future. We're at least a decade or more away from that kind of determination.
All right, so then the follow-up question to that is, if the search for life 2.0 is potentially the most interesting or more important discovery, why are we spending so much time and effort and resources searching Mars? Wouldn't it be better to search someplace like Europa or Enceladus?
I agree that if finding a second genesis of life was the prime directive, then looking for life on Mars is not the very best way to address that question. And that's because we know that rocks can travel between Mars and the Earth. Now, they're more likely to go from Mars to the Earth, in which case we would all be Martians, than the other way around. But still, the issue remains that there's very inefficient but somewhat effective interplanetary transport of rocks and material, which could contain life because it's shielded by being inside a rock. In that sense, yes, Enceladus and Titan are probably the prime targets, along with Europa. So I'd elevate those three objects in the outer solar system to a very high degree of interest. And if you're really interested in Life 2.0, a low probability bet, but by far the most interesting bet, is Titan, because their biology would have to be based with a different chemical basis. It would be based on ethane, methane, some amount of liquid water, ammonia, acetylene, all sorts of very interesting chemicals in the lakes on Titan. So that's very different from terrestrial chemistry, and the biology that might result from that, which nobody knows if that's possible at all, would be very different. So if you just wanted to swing for the fences with Life 2.0, you'd go to Titan.
Thank you very much. Prachi Sharma, 25, asks, is there currently any evidence of wormholes?
No evidence of wormholes, and actually it'd be hard to know exactly what to look for. So wormholes are theoretical concepts in general relativity, basically, connected with the idea of black holes, where space-time has a convoluted structure such that one region of space-time connects to another region of space-time, a sort of a direct portal between very physically separated locations using rupture in space-time, or a tunnel if you like. So that's the idea of a wormhole. It's possible in principle because in general relativity space can have a convoluted structure, and you can easily imagine a convoluted structure that includes wormholes. The space of our universe, however, is generally very simple and smooth. The galaxies distribution mapped out and the way light travels show us that space is flat on large scales. So the only place where space is highly distorted or convoluted is in black holes themselves. But there is no reason to believe that a black hole somehow connects to another region of space-time. That's beyond the realm of really reasonable theorizing because there's no reason to expect it, and it's certainly beyond the realm of testing because the event horizon prevents a barrier to information such that we don't know what happens on the other side.
The next question is from Lawrence 4040, who asks, if solar fusion forms neutrinos, I assume that antineutrinos are also formed. And if so, what is it that neutrino detectors are looking for? Is this just another example of cosmic asymmetry?
Yes, there are cosmic processes that form neutrinos and antineutrinos, and on balance and overall in roughly equal numbers. Antineutrinos, like other antiparticles, if they encounter matter, normal material of any kind, they will annihilate to create gamma rays. Interaction strength of neutrinos, though, is very low. So the interaction rate of antineutrinos with normal matter to form radiation is also very low. And actually in practical terms, we have much closer, much better ability with big detectors using large amounts of, for example, cleaning fluid as a common neutrino detector, but there are other fluids that are used in deep mine detectors. They're much easier to detect neutrinos. The interest for the neutrino detection world is that there are three flavors of neutrino: the electron, the muon, and the tau in increasing mass. We don't know their exact masses, and they oscillate between the flavors. That's been proven already. But we don't know the masses of the three generations of neutrinos. So that's where the current field rests, and that's what we would like to know, what the masses of those three families of neutrinos are. And that would allow us, for example, to rule out neutrinos as being important in the creation of cosmic structure in the universe, because they would be a version of hot dark matter. We think they're not important in that regard, but we don't know until we measure the mass more precisely.
The next question is from G. Bruzon, who would like to know if there is any evidence of dark matter on Earth.
There is no evidence of dark matter on Earth, but there should be dark matter on Earth or around the Earth, because dark matter, weakly interacting particles, they don't interact through electromagnetic forces, but only by gravity, should permeate space, and that includes the space around the Earth and the Earth itself. So the evidence for dark matter on Earth will come from detectors that have been built, mostly down deep mines, to shield from other particle events that would be a confusing signal. There's over a dozen of these dark matter detectors that are located in deep mines in various parts of the world that are currently just gathering data and have been quietly gathering data for years, that are going to try and detect the flux of dark matter particles that is present, around us all the time in this part of the solar system, in this part of the galaxy and the universe. So we will know about dark matter on Earth when any one of these detectors is successful. None have been yet. There's hope that they might be within a few years. Otherwise, there will be a crisis in cosmology because dark matter will not have the properties that we appear to think it needs to explain the large part of the universe pie chart that it represents, which is about 24%.
All right, getting to some current space news, and this is on Roxoa's mind and probably a lot of other people's mind as well. What are your opinions on the Starship project by SpaceX that had its maiden test flight yesterday and had a spectacular flight, but a kind of abrupt landing? Where do you think that's headed?
Yeah, I mean, Elon Musk is gearing up for a Starship, a large human-bearing craft that could go to Mars. I mean, and literally carry hundreds and perhaps in the end thousands of people. This is it's an impressive technology, but it really just scales up his Falcon 9 rocket, just increases the number of those engines to create an enormous lift capacity. So it's a very large vessel. This was not a fully fledged prototype of his Starship concept. This was just an early prototype just to see what its properties in flight would be, because it's the aerodynamics of it before it leaves the Earth's atmosphere are quite important. The problem came on the landing. He didn't manage a landing and it broke up. It was quite a spectacular failure. But that's happened before with SpaceX. The first time that Elon Musk tried to land one of his reusable rockets on a platform in the Gulf of Mexico, it spectacularly failed and was caught on video, and Musk posted the video that same day. He's not ashamed of his failures because he knows that he's doing very ambitious things and there's going to be a certain learning curve and a certain failure rate. So as with yesterday's event, he's not deterred by this, and his commitment and SpaceX's commitment to this vehicle is pretty strong. And now that they're getting money, their business model is much more viable than it was a few years ago because they have successfully delivered supplies to the space station for several years, and recently astronauts to the space station. And NASA is giving them contracts of multi-billion dollars to do so. So SpaceX now has a revenue stream that will allow Elon Musk to put development money into his most ambitious project, the Starship.
Yonk, who's on with us live, would like to know, how does one calculate the radius of a galaxy? And yeah, let's start with that one. How do you calculate the radius of a galaxy and then our galaxy?
Right. So what's the size of a galaxy? It's a good question because galaxies don't have sharp edges. You see images of galaxies all the time on the internet or from Hubble Space Telescope. And whether it's an elliptical galaxy or a spiral galaxy, any galaxy, they just sort of tail off into space. So they don't have sharp edges. So astronomers, when they're characterizing galaxies, they have to use a different measurement because it doesn't have a size like a physical hard-edged object has a size. And typically, astronomers use a size that might represent what they call the half-light radius. That is the distance out to which, within that radius, half of the total light of the galaxy is, or a radius that encompasses 90% of the total light of the galaxy. And since they don't have hard edges, the question becomes, well, how do you know what the total light of the galaxy is anyway if it doesn't have a hard edge? And so what astronomers do is they make an image and they make a model. They make a two-dimensional model of the light distribution of the galaxy, and they can sort of extrapolate that model to a point where it converges, and that tells them they've been able to encompass the total light of the galaxy in a model, and then they can characterize it in terms of these different sizes. But they're not an edge size in the normal way that we think of an edge.
As a follow-up to that question, how do we calculate the distances between two objects in space?
So the distances between two objects have to be calculated in 3 dimensions. So 2 of those dimensions, of course, are where the objects are in the sky. So for example, we see 2 galaxies on the sky, and we can calculate the angular distance between them. Then we need to know the radial distance to them, which is determined by the redshift. So you take the redshift, you know what the expansion rate of the universe is, and you can use that to calculate a distance in millions of light years or megaparsecs. And so you've got distances separately measured for each galaxy from its redshift, and that gives you its radial distance between the 2 objects. And then you, of course, can just use simple geometry to combine it with the angular distance between the 2 objects to get a 3-dimensional distance. So that's how it works in practice.
Excellent, thank you. The next question is from Keith R. Crum, who would like to know, what can we learn from the history of astronomy? For example, how do we avoid mistakes like the ones made by Percival Lowell?
Yeah, there have been mistakes in the history of astronomy. It's a good point. And the one that Percival Lowell made was a very particular kind of mistake. It's not a routine scientific mistake. Percival Lowell, who was not trained as a scientist, but learned a lot of science. He was a businessman who retired and was always interested in astronomy, a keen amateur, you might call him. And in his retirement, he funded the creation of a large telescope at Lowell Observatory, and he was obsessed with Mars. Unfortunately, his obsession tilted him over the edge of proper scientific method. So he came to believe that the markings he'd seen on Mars with telescopes represented the traces of a dying civilization on Mars that were using canals essentially to carry water from the ice caps towards the equator where they lived. And he was wrong. These features were not as linear as he thought they were, and the backstory he imagined of the Martian civilization was unsupported by other evidence. So Lowell's mistake in the history of astronomy is a very particular kind of mistake, because he essentially let his fantasy, if you like, his wishful thinking of the fact that there might be life on Mars, color the way he interpreted the data he saw through the telescope, and it misled him. And he was using selective data in that sense too, because there were clearly observations at the same time that showed that these features were not linear. So he was using wishful thinking on that too. Now, generally, scientists don't tend to make that kind of a mistake. That's a pretty rare mistake in the history of astronomy. More often, however, scientists make mistakes by having data that's not as accurate as they thought they had, or data that's subject to a systematic error. That's a very hard kind of error to control because it doesn't go down in size if you take more data. So systematic errors, unrecognized errors, underestimating errors, those are the real ways that scientists make mistakes. And yes, occasionally scientists are overly attached to a theory or an idea, and they, again, use bias. They put bias into their interpretation of data to support the theory they like, and that does happen.
And kind of related to a previous question, a couple of people would like to know if you can talk about what a parsec is and what's the benefit of using parsecs over light years.
Yeah, parsec is the preferred astronomer designation for distance. It's the unit of distance. It's typical of the distance between stars in the solar neighborhood, so it's a useful characteristic of star-to-star distances. Parsec is an abbreviation for a parallax of 1 arc second. It's just a compression of that phrase. And that refers to the fact that astronomers measure the distance to nearby stars by the parallax method, which is observing a star when the Earth is at opposite parts of its orbit, and then measuring the apex angle of the triangle when you draw a line from the Earth at, say, December towards that star, and the Earth from June to that star. You get a long skinny triangle, and the apex angle is the parallax. So a parallax of 1 arc second is the definition of a parsec, and we know it to be about 3¼ light years. So you can convert it into light years, but for astronomers it's a more fundamental unit because it relates to the way we measure distances in astronomy.
Excellent, thank you very much. The next question is from Athira Ramesh, who would like to know, with the great conjunction that's happening on December 21st, Um, will it be visible all over the world, and does it have any astronomical relevance?
The conjunction, I should say, before going on, is an impressive alignment that we're going to see in a couple of weeks on the winter solstice. Actually, it'll be best visible between Saturn and Jupiter, two great gas giant planets. And they will be very close in the sky, closer than is at all normal, by I think it's 1/10 of a degree apart. Remember, the moon is 1/2 a degree in angle, so these are going to be very close, and they're bright night sky objects. It's quite a dramatic. They almost look like a double star to many people. It's very unusual for them to be that close, because if you think about it, they both have multi-decade orbits, and so they move at different speeds in their orbits. The odds of them even coming into the same part of the sky, it doesn't happen very often, every century or so, or dozens of years apart. So to have them this close is a particular alignment that is really quite rare. And in fact, the last time it occurred, I think, was in 1226 in medieval times. The next time it occurs is not quite as far ahead in the future, but again, most people alive now will not see it. So this is your once in a lifetime chance to see this alignment. Does it have any underlying astronomical meaning beyond an alignment? Not really. These objects, even when they're that close in the sky, are hundreds of millions of miles apart in space. And so there's no particular gravitational effect or effect on the objects by the fact that they appear to be this close in the sky.
All right, the next question is an excellent one from Christina Vislapu, who sent an email. Now, I'm not sure of the premise of her question, so we'll have to kind of address that first, but I think the rest of it will pan out from there. So she says, during the time Jupiter was on its journey to the inner solar system and back, the inner solar system was swept clear of up to 90% of the rocky material, and with just little crumbs remaining, our 4 terrestrial planets began to form. The question is, what happened to the 90% of the rocky material that would have instead formed super Earths instead of the small terrestrial planets?
Right. It's a good question, because it alludes to the fact that as we learn more about exoplanets, we have cataloged their different sizes, and we realized that the solar system is a little unusual because we have 4 terrestrial planets, 2 of which are essentially Earth size, because Venus is close to the Earth size, and Mars is quite a lot smaller, and Mercury is a very large amount smaller. Out in the rest of the Milky Way that we're finding exoplanets, super Earths are common category. Essentially 1 in 4 extrasolar planet systems has a super Earth, and many have more than one. And there are no super Earths in our solar system. So it does make people ask the question, was there anything particular about the formation process of our solar system that would have led to no super Earths? And the question alludes to one of the mechanisms by which we can explain the fact that our terrestrial planets are all quite modest in size. The migration of the giant planets, both in and out in the early 100 million years or so of the solar system evolution, acts as a gravitational sweep or broom of material. So the answer to the question of where that extra material went that could have been part of making more massive terrestrial planets than we have is that it was swept clean of the solar system. It was given essentially an escape velocity by the enormous gravity of Jupiter. So Jupiter has the power to eject objects from the solar system as a sort of gravitational slingshot mechanism.
Excellent. Thank you very much. The next question is from Zalgbo, who's on with us live. Is it possible that there are elliptical star systems, kind of like elliptical galaxies, or are star systems always disk-shaped?
Well, star systems, I'm not quite sure the reference of the question. I mean, galaxies.
I think he's talking about solar systems, like planetary systems. So is it possible that there are planets that go around a star like in 3 dimensions rather than all of them being on kind of a flat plane?
Yes. Okay. So that's an interesting question. Well, what are the range of orbital properties of exoplanet systems? Do they all have the equivalent of our situation where the planets orbit in a plane, and that's in the ecliptic on our night sky? The answer is not exclusively. There are a few exoplanet systems that have been found where the planets have quite a large orbital tilt from one to the other or among them. There are even some where there are a few planets that are orbiting in one direction, and there's one that's inclined and counter-rotating. That's very rare, but that does exist. So the simple answer is that most exoplanet systems, as much as we can measure this, because it's not easy to measure, do appear to be more like our solar system. They have an equatorial plane. The planets seem to orbit in the same sense in the equatorial plane. But there are exceptions, and a significant number of exoplanets have been found with high orbital inclinations. And the question of how that happens, it's often attributed to a situation of the formation where there were strong interactions between massive planets. It could happen after formation. If there was a close passage of a perturbing or disturbing object that was massive, you could dislocate or trigger a change in one planet's orbit, or maybe the whole system, just jostling it up gravitationally. These are very interesting systems, and we don't know the answer to how they get that way or really how common they are, but they do exist.
Our next question is from a live viewer, Mohan46. What is your opinion on the recent claim by a retired Israeli minister that aliens have contacted Earth and that the administration in the United States is aware of it?
This is a claim that's part of a large category of claims that has persisted really for decades. That aliens have visited the Earth or contacted government officials or countries, or the military have been aware of communications, and we haven't heard of that because it's secret. It's in the general category of a conspiracy theory. So, I mean, I'm skeptical. Scientists should always approach something skeptically, and especially something with such profound implication as contact with an extraterrestrial civilization. Apart from the fact that I just don't think governments, Israeli, American, or any, are able to keep such a massive secret as this, I think the evidence that would be required to believe it is true is not really present in any of these reports. So we hear occasionally, it happens in the US quite frequently, there's been a spate of releases of videos from the Air Force that purport to be UFOs that are alien spacecraft, for example, and so on. That's how all happened in the last year or so, and the government is tight-lipped about it and just says, no, we have no evidence of alien visitations. They do, however, claim that there are UFOs, unidentified flying objects, that sometimes have strange attributes in the way they move. Okay, so there may be something to investigate there. But as for the fact that there has actually been true contact with aliens, I simply don't buy it. I mean, obviously, the only way, if you hide behind a conspiracy theory, then you can claim it as long as you want. But in the end, it's not a meaningful part of the scientific world until we get the information released. And if there's no evidence, then no one's going to believe it.
Excellent. Thank you very much. The next question is from Texadactyl, who says, on Titan, isn't there some evidence of water underneath the green goo? But I assume they mean water underneath the surface, because I don't believe there's any goo on Titan.
No, well, there is water. Water is a component of Titan. And remember that Titan is at a distance from the sun, that the surface temperature, even under a protective atmospheric layer of nitrogen, is incredibly low, and it's 150, I think, degrees below the freezing point of water. So there's no immediate way you could have liquid water on Titan. The exception, however, and it's an important exception, is that Titan has cryovolcanism, which is to say there's internal heating of Titan. It's not large enough to be a fully volcanic moon, but it has tidal heating caused by its parent planet, Saturn, and that tidal heating plus radioactive decay that occurs naturally within rocks is sufficient to create under the surface at the base of these ethane-methane seas mild volcanic activity. So there's magma that's flowing, there's energy that's flowing, and so at the base of these seas, the temperature could indeed be sufficient that there's water mixed in with the liquids. So I think there's water there, far below the surface. And what's the chemical state of that material, and what could happen in water that has a more sort of temperate temperature than the deep freeze of the Titan surface? Nobody knows. We'd love to know. It's why we need to go back to Titan.
The next question is from Athira Ramesh, who is kind of referring back to our discussion earlier about astrobiology. So can you talk about the idea that, at the early formation of the Earth, something, he said an asteroid, but something might have hit the Earth that had life on it or in it that could be from some alien planet. And so, these life forms might be on Earth and somewhere else. Can you talk about that idea and how that could happen and why that's interesting or important?
Yeah, the idea that life travels or through space between planets or even between solar systems and seeds itself that way is called panspermia. That's the general name for the idea, and it goes back a couple of hundred years, actually. The evidence for panspermia is lacking. There's no evidence that life on Earth started anywhere else than the Earth. We do know that impacts of material and deposition of material in the early solar system did produce, or rather did add to the Earth's surface important ingredients for life, including potentially amino acids, but certainly including phosphorus-bearing compounds. Phosphorus is necessary for the formation of ATP, the energy storing mechanism of life, and phosphorus in cosmic terms is quite a rare element. So seeding the Earth with phosphorus-rich material is important, as is, of course, water. And there's a debate over whether most of the water came from beyond the Earth or bubbled up from the mantle and the deep Earth, and it doesn't really matter. In the end, we did need water to have life on Earth. But there's no evidence that life is transported between planets, and less so between solar systems. The odds of life traveling between solar systems are essentially vanishingly small. People have done this calculation, apart from the fact that the life would have to survive intact inside a rock traveling for probably tens, maybe hundreds of millions of years through deep space. Traveling within the solar system is certainly possible. And rocks can travel from Mars to the Earth. We know that because we have Martian meteorites on the Earth, over 100 that have been cataloged, and probably many more that haven't been found yet. So it is conceivable that life on Mars formed early and seeded the Earth life 4 billion years ago. It's going to be a very hard job to prove that, though. But more generally, I don't think life moves around in astronomy or in solar systems or in the universe in general by this mechanism.
The next question is from Ace's Hammer. What would be the options if there was a sizable asteroid found to be heading on a direct collision course for Earth? Is there an action plan for that kind of situation?
Yes, there are action plans. It's good to know there are action plans. And the U.S. government, working with NASA and consulting with a lot of scientists who know this field, have produced pretty much an action plan. I mean, the good news is that the surveillance systems, which the U.S. government tasked NASA with finding all objects larger than about 150 meters that might potentially hit the Earth, that cataloging is complete. So we have an inventory of the objects that could cause more than regional devastation on the Earth. And the network is good enough that if one were heading towards the Earth, our lead time, our advance notice, given the speed they travel and the distance it would be picked up at, is several years. So this is not going to be a nightmare scenario like in a movie where the clock is ticking and you have an hour or a week to figure this out and do something. You're going to have months or actually probably a couple of years. If you have that amount of time, the easiest and most reliable way to deal with the problem is to send out a large, massive space probe. It's got to be massive to do the gravitational tractor job that it's designed for. And you send this space probe out to eventually turn around and track the asteroid, land on the asteroid, and tether itself to it. I mean, there are ways to do detonation or drilling that you can attach a spacecraft to an asteroid or a fast-moving object, and then use retro rockets to alter its trajectory. So you can just use rockets that are on the spacecraft once you've attached it to the asteroid to subtly alter its trajectory. And if you do this with enough lead time when it's still far away, you don't have to alter its path by very much. A second way of doing this is by what's called a gravitational tractor, where you use the spacecraft itself, which will have to be quite massive because asteroids are massive, to just go alongside the incoming asteroid, parallel to it, and just slowly deviate it by gravity. That's actually a less efficient way to go than using rockets. So I think people will use rockets. The thing you don't do, just to mention it, is you don't blow it up. I mean, that's Dr. Strangelove. That's sounds fun to blow up a big thing like that. But of course, if you really just detonate it head on, for example, all the pieces you create will continue more or less with their same trajectories heading towards the Earth. So instead of one huge problem, you've created a set of medium scale problems all peppering the Earth at the same time. So that's the thing you don't do.
Excellent. The next question is from Single Coded. Would like to know, and I think this has come up a couple of times, is there still a place for either philosophical or humanistic approaches in modern astronomy?
Absolutely. Astronomy, for example, is very close to natural philosophy, which was the term for physics, at many universities going back centuries. And the philosophical foundations of the subject are very important because we don't know the profound answers to the nature of the universe, truly where it came from, whether there's life in the universe and we're alone. So there's some foundational questions that are completely up for grabs. And so having a philosophical approach makes a lot of sense because we don't even know necessarily what the best method is for solving these problems. Astronomy invents its own tools, its own observational mechanisms as it goes along. And so a philosophical approach is valuable. And so is a humanistic approach because the issue of life in the universe puts that right front and center. Humans worry about their nature, their place in the scheme of creation, their fate, their role in the universe, and astronomy is in large part designed to answer that question. And so that takes a broader approach. There's plenty of room for a humanistic approach when considering that. And also for the reason that astronomy is part of people's lives. Unlike chemistry, which most people don't experience on a daily basis, or even physics, astronomy deals with the night sky, the objects of the sky, a very direct sense of our loneliness, our place in the universe, and the vastness of it. And so that inspires humanistic approaches. So I think the field is very amenable to such ways of thinking.
The next question is from Hernan as well. Last session, you talked about the Voyager Golden Disk and the Pioneer Plaque. At the speeds these probes are going, it'll be tens of thousands of years before they reach the nearest star. Did anyone seriously believe that it would lead to any sort of interstellar communication, or was it just meant to be a symbolic way of throwing a bottle into the Pacific Ocean?
I think it's a good question, and I think the answer is clearly the latter. I think, as pointed out, these objects are traveling fast for a human-made object, but slow compared to interstellar distances. And so they're literally tens of thousands of years before reaching the nearby stars. And people have done the math, and it's actually more like hundreds of thousands of years before they really get close to another star system. They weren't, of course, targeted in any sense like that. They were doing work within the solar system, so the direction by which they exited the solar system was not designed to align with any nearby star system. So no, it was never a direct attempt to take our message to another star system. It was a symbolic, a metaphoric act of us saying, we're here, this is our first human exiting of the solar system. That's a pretty important act, and we wanted to attach to the spacecraft some attempt at communication or saying who we are and what we stand for. And of course, the act of putting together the messages and the images, involved a number of scientists. The public was engaged with that process and sometimes inspired by it. So it was a way of bringing the public on board with the idea that we could communicate in the universe, even if this wasn't really a practical attempt at communication.
Mile High AP asks, if someone were newly entering the field of astronomy with a deep interest in studying dark matter or energy through advanced computer modeling and possibly like deep learning algorithms, would you recommend studying astronomy or astrophysics alongside computer science?
And the distinction between astronomy and astrophysics is a subtle one. I'm in a department of astronomy. Some of the departments that are just like my department are called astrophysics. Some are physics or astronomy groups within a physics department. So the triangle of physics, astrophysics, and astronomy is is quite a tight one. So I don't think that word makes much distinction. But for the work you're asking about doing meaningful modeling of dark matter, I think you need the tools of astrophysics for that. You have to work with obviously a good knowledge of gravity, a good knowledge of how to conduct a simulation. Also, perhaps the use of hydrodynamics in the simulation if you're encompassing gaseous regions of the universe as opposed to just particles interacting by gravity. So for doing a dark matter exploration like that through simulations, then quite sophisticated computational techniques are required, but also a pretty deep understanding of astrophysics, which implies going through master's level training in the subject.
The next question is from Bill 3649. I think it's a great opportunity to talk again about the Big Bang in the universe. Do we know where the Big Bang occurred? In other words, can the Hubble Space Telescope be pointed in one direction and see light emanating from where it was, whereas if it's pointed in another direction, it wouldn't?
No, it's a good question, but no, we cannot identify the center of the universe or the place where the Big Bang was. The simple but slightly annoying answer is the Big Bang is everywhere. The Big Bang is around us because all parts of the universe were at one point in time in one place, and then they expanded. So if every galaxy is moving away from every other galaxy, no galaxy is the center of the expansion. Similarly, if we look out in space in any direction, we see roughly the same set of galaxies, not the exact same galaxies, but the same distribution of galaxies. And as we look further and further out in space, we just look back towards the Big Bang, we just see back towards the time when galaxies were forming. But it's the same view in every direction. We see the youngest galaxies and the age of formation of galaxies and eventually the dark ages of the universe by looking out in any direction. So again, the Big Bang is going to be out there in every direction because we are a part of the entire expansion ourselves. And so it's not outside of us or in any particular direction.
The next question is from Bardia Khandani. Does the type of nuclear fusion in a star affect the possibility of living organisms' existence in its surrounding planets?
Indirectly, in the sense that the fusion process inside the star creates the luminosity of the star and its radiation, and that combined with the distance of the planet from the star says what the temperature, the equilibrium temperature on the surface of the planet will be. So yes, the fusion process in a star determines its luminosity, and its luminosity combined with the distance to a planet determines the temperature on that planet, which presumably has to be in an equitable range between the freezing and boiling points of water for us to expect biology like we see on the Earth.
Excellent. The next question is from one of our live viewers, Sarcastrophe 143, asked, how does the mass of a black hole relate to its parent star's mass and parent star's core mass?
That's an interesting question because stars go through a long and complex path or a long life with different stages before they get to a black hole stage. The simple, and there's not a hard-edged answer to this question. Basically, on its way to forming a minimal mass black hole, which would be about 3.5 times the mass of the sun, the star is going to lose most of its mass. So the stars that are presumed to give the lowest mass stellar black holes we can see started off life at about 20 times the mass of the sun. And in the process of their life, in their late phase of normal evolution, they blow off gaseous envelopes. So they blow off some of their outer layers. And then more dramatically in the supernova phase, which precedes the formation of a black hole, most of the rest of the mass is left. So you can see that a star that starts as 20 times the mass of the sun is losing close to 90% of its mass to leave behind the black hole that's 3.5 times the mass of the sun. And it's about the similar math for other black holes. More massive black holes were even more massive stars when they started and also lost most of their material into space.
The next question is from Mile High AP. Do you think it's more likely that the universe is ultimately simple and that our understanding of dark matter and energy will eventually fit this mold? Or do you think a complicated universe is more likely, say one with multiple dimensions and really complicated underlying physics and that kind of thing?
That's a very interesting question. Is the universe simple or not? It's a very profound question of science, actually. It's almost a philosophical question. I think we have to say that it's not obvious we have any right to expect the universe to be simple or as simple as our simplest models. There's a predilection in physics, especially stemming from theoretical physics and particle physics, to imagine that the ultimate nature of matter is simpler than the proliferation of different particles we see, and therefore that the universe may fundamentally be simple too. But there's no reason that has to be the case. That's based on almost an aesthetic principle. And it's also based on expedience, because if the universe was too complicated and subtle, we might never be able to figure it out. So I think we can all see that it's hubris, or almost ego, that would lead us to believe strongly that the universe is fundamentally simple and we just have to figure that out, when it might not be true. It simply might not be the case. We have to be prepared for the fact that it may be hard to figure some things out. The physics, the mathematics, they may be too challenging for us, and the universe may resist our urge for it to be simple. As for the current situation, I think the jury is out. There's still a strong belief, based primarily on physics, as I said, that there's underlying simplicity in the cosmos. But there's evidence from the data we gather that things are messier than that, and they may not be fundamentally simple. There's a tension between these two ideas.
All right, we have to end just slightly early today. So we have one normal question, and then hopefully one that's a very short one about another project that we're working on. Yonk, for Yonks, would like to know, is it at all possible for a companion star to survive a supernova explosion?
Yes, it is. If the binary star where one of the members was a supernova is a wide binary. So binary stars have quite wide degrees of separation. And so absolutely, if a star was not in a tight binary with a supernova, it could survive a supernova explosion. Even fairly tight binaries could survive it, because the star's self-gravity, the companion self-gravity, is such that supernova may blast off part of the atmosphere of the star, but not completely disrupt it. So we do think normal stars can survive a supernova relatively nearby. That's the same as not true for life on Earth, if that happened, however.
All right, the final question is from Nastro Crochet, who would like to know what the status is of our new history and philosophy of astronomy course.
Okay, glad you asked. Yes, we're looking forward to launching our fourth total MOOC, our third for Coursera. It'll be the history and philosophy of astronomy. All the videos have been filmed. They're in the can. I've been teaching using those videos at the University of Arizona for a 300 level class, and it's gone pretty well. So we have all the videos. Matthew and I and a very smart young undergraduate, Maria, have been working on evaluation materials. And so, and we put up, pieces of the material onto Coursera, built the sort of shell, if you like, or the framework for that course. So I wouldn't dare to put a launch date on it, but if I had to, I would say March 1st. That's probably a safe launch date, but we'll definitely be launching this course in the spring, and we'll talk about it then, closer to the time. So thanks very much for all your questions. They're good as always, and to Matthew and Vicki working behind the scenes and on the scenes to make this work. And we'll be back with you next week.
Excellent. Again, we're going to post a link for how to link your Amazon Prime account to your Twitch account and subscribe to the channel if you'd like. And then for those of you who become subscribers, we're going to have a giveaway. We have a signed copy of one of your books, Chris, one of your many books. We're going to give away to one of our subscribers. So make sure you do that. I can't remember the cutoff date. Vicki will probably type it in the chat. Thanks for joining us today, everybody. Have a great one.